Let me stop. So let's try to clarify each like the term by term. So, but let me just reorder the terms in a way that you can understand each concept in the smooth way. So the part of the necessary understanding is all related to the Hopf vibration first. So this construction matters very in a very concrete way. So the definition was so you start from S3 inside of C2. And then we define a map. We define a map in a way that so we pick arbitrary element from S3 so that you know it satisfies the equation of the sphere. Is that okay? Equation of the sphere. And then what you have is so you assign each element to, let me first specify the notation for the element first, and then try to connect what you know so that we assign so-called the homogeneous coordinate. So this is defined as a collection of the lambda times z1, comma lambda times z2, where this lambda is c outside of the zero. You know what I mean? So that's the definition. And from the problem set two, what you learn is this is so-called coming from the quotient of the group action. So here, so we have the group G, which is S1 in C1, act on S3, sit inside of C2 in a way that e to the it acts on Z1, comma Z2 in this way, as you at this point, I assume you two feel very familiar with it, so that we define this guy, and S3 quotient by this G, or S3 quotient by, in this case, S1, is just the collection of the orbits. Is that okay with you? Collection of the orbits. So if the terms are not like the concretely like the clarify for any of you, please let me know. So that's we put this as a domain, codomain of the function pi.
Could I
And
ask
yeah,
could I
yeah.
ask for the S3 quotient G bit? Is that basically like that's how we assign the whole orbit to a single point? That's what we're doing there, or that
Exactly. That should be your like the correct like the intuition. So I'm really bad at drawing. So but you should think of S3 as a indeed a three-dimensional sphere first. So this is not in R3 but in R4. Is that okay with you? And then you choose the point C1, comma Z2 like this, C1, comma Z2, and the group action by S1 give you the gray circle like this. So this guy is now regarded as a Z1 versus Z2 this way, this way. And then we collect all those like the gray circle or the orbit as a one single element. And that collection is S1 quotient out by S3 quotient out by S1. And Hopf vibration says this becomes S2, which is same as also. So, but let me just make sure that you really understood. So S3 quotient out by S1, this is the definition of the CP1, first of all. This is definition. So, and as you know, we train this structure by introducing another like the exponent, right, for our own purpose. And then this is a little bit non-trivial, but this is just the consequence of the Hopf vibration structure. So Hopf vibration tells us that this indeed, it becomes S2. So that's why we identify Bloch's sphere as indeed a sphere, but the reality is actually that's CP1. It's defined as a S3 quotient by S1. That's the collection of the orbits. Is that okay with you? So now let me just go back to the question of the the Jason. So definition of the vibration. This is a very good question. So um, all you need to know is this map pi. Is that okay with you? This map is now given. So I want you to now think this map in the following way. So you have the map from S3 to S2. Is it okay with you? S3 to S2. So that the vibration means, so take any point P from S2. Let me make sure you can identify S2 as you know as a CP1. That's fine. You can identify this as a S3 quotient out by S1. Either cases would be okay. You choose arbitrary point from the codomain. It's okay with you? From the codomain. Then the definition of a fiber denoted by pi inverse of p. So this is a common notation in mathematics. So this is a notation which is defined as collection in S3. So element in S3 satisfying pi of Z1, Z2 equals P. Of course, Z1, Z2 pair is the element itself. If you feel a little bit like the unknowing, then you can write like this, but it's just a matter of the notation. Is that okay with you? So if you want to just regard this as just Q, I'm just saying pi of Q should be P. So we are collecting all of the Q that maps into the element of P. So
Okay.
I want you
Okay.
to imagine how it looked like. Can you imagine how it looked like? So you start from the one element on the Bloch sphere and you take the pullback, yeah, orbit. So that's the fiber.
Oh, sorry. Yeah, I asked ChatGPT for this definition, but from what I understood from it, it's basically like a group or a quotient, but you map it to a specific point
Exactly.
on the
So
on a different topology or whatever.
yeah, so exactly. So the properties. So I'm not sure that how many like the properties I need to list here, but let me just say properties for a moment. So so pi inverse of p. So from the definition, it is clear this is the subset inside of S3. Is that clear? Because we collect the elements from S3 indeed, but at the same time, so this is a very fancy notation, and I recommend you to also you can use this fancy notation. At least the math faculty will very like it. So this is not exactly equal, but this tilde notation we identify as the same. So you can say isomorphic. This is a very fancy term in mathematics. This is a math chem, so you can use this term. Isomorphic to S1. Of course, it depends on P for each P. But I want you to see that because this is coming from the group action of S1, so even it depends on the choices of P, so it will give you the S1. Is that okay with you? So that's why now if you just combine these two properties, you can, so please just understand what this notation means. S1 is in S3 even though it seems not really make sense in a way that S1 is a subset inside of C1, whereas S3 is subset inside of C2, so that you might feel, oh, well, how that makes sense. This means we already identify pi inverse of P as S1, and that's this is the subset inside of S3. Is that okay with you? Yep. And yeah, please go ahead, Jason.
I was going to make like the comparison, like if it's like before, it's like we're mapping the great circle, which is technically in this S2, but this time we're moving up to S3. The great circle is still there.
Yeah.
It's just, yeah.
Exactly. Yeah, now you have like correct the intuition. But let me make the notation in a fancy but standard way so that instead of using the classical notation of the subset, so people prefer to use this type of the arrow notation. Does that make sense to you? So arrow notation means the circle sit inside of S3. This is the same thing, but we just change the notation. Does that make sense to you? So this is also the same as pi inverse of P sit inside of S3. So usually this is called by embedded. You can say so the fiber is embedded into S3. You can say that. And this fiber is just the same isomorphic to gray circle. So you can therefore say that gray circle is embedded into S3 from the orbit. Is that okay with you? So now let's just combine our facts. So consequently, so now let's just combine what we have learned. So from the Hopf vibration, you start from S3. Agree? You have S3. So we have a map pi that maps to the Bloch sphere. Is that okay with you? We have a Bloch sphere. So that you can also consider the fiber. So you might see this from the either the Wikipedia page or anywhere else. This notation means that so each of the fiber is the subset inside of the S3. That's the what this notation means. So that the reality this guy is just pi inverse of P for each P that we call by the fiber. Does that make sense to you? So that's clarify one question in my opinion. So up to this point, so I should move on to the part of the global quotient because I need to explain what's the difference with the structure of the orbifold. So yeah, so I assume up to here I clarify everything about the fiber. Is it okay with you? Fiber is now very clear. So the next thing is about the global quotient. And you can introduce also this term in your presentation, smooth manifold. So let me say this. So example and non-example of let me say smooth manifold. So this MFD just means that I'm just lazy and usual expert just skip to write everything just concretely. So so Hopf sorry. So Bloch sphere is a smooth manifold. Even we should talk about the definition first, but let me first provide the just the example, non-example. So non-example, weighted projective line is not a smooth manifold
because
because
of singularities.
because either you can say the presence of singularities, as you said, you can say so. This is legally fair, and or equivalently, I should say, equivalently, the lack of global quotient that from now on I should explain. So the term regarding the global quotient, so you need to connect this term with the so-called smooth manifold, this term. And this is important for this like the understanding because we'd like to change the Bloch sphere as a weighted projective line in general. This is no longer the smooth manifold, and this affects the actually this is actually changes the situation completely. Is that okay with you? So now I need to explain what those are if you don't have any other questions here. So first, smooth manifold. So this means so it is I'm a little bit hesitated to put every like the term concretely, but as I like heard from Jason today, is because he took the topology. So let me use the term. So this is a topological space. So if you are not familiar with this like the term, you can kind of just skip this guy. That's completely fine. So you can simply just say a space. That's fine. But rigorously speaking, I should say a topological space. Topological space, locally same as our Euclidean space. Let me explain what this means. So this is the definition. Euclidean space as an Euclidean space. So i.e. for any point in a smooth manifold, there exists a small neighborhood, at least, containing this point that can be identified as a small ball in Rn. So let me explain this like the fancy, like the description with the picture. So let me draw three different like the pictures. So examples of smooth manifolds. So if I draw R2, if I draw R2 first, then if you choose arbitrary point, for example, if I choose the origin, then RS is very clear that you can just identify this ball as a ball in R2. It's just a That's a dumb, it's like the sentence. Is that okay with you? But this can be done for each point. Whatever point you choose, you can identify this neighborhood as a ball in R2. Is that clear? This is very like the silly to say it. So if you just now look at the sphere, if you now look at the sphere, so I kind of convince yourself that this at least structure would be different from R2, kind of. So even though we don't really see the next like the terms why those two should be distinguished, but S2 is definitely different from R2. Is that okay with you? Kind of. So but still what you can do is whatever point you choose, you can still identify at least one small neighborhood as a ball in R2 so that you can identify these two are identified in this way. So you can say the smooth manifold means locally Rn, but not globally. So the global structure of the S2 is clearly different from R2 globally, but locally you can identify as just the same as R2. So if you draw, for example, the torus like this, so my drawing is very bad. So it is clearly different from R2 globally, but locally, so if you just choose arbitrary point on the torus, so you can kind of convince yourself that you can identify this ball as a ball in R2. So those are the examples of the smooth manifolds. Is that okay with you? So, and by the way, so the reason the global quotient play a role in is following the reason so that you can see that this is same as CP1. CP1 is same as S3 quotient out by S1 globally. Globally, so that these two are now the same. So
So does
go ahead.
I was going to ask if globally means so you're just applying this to like all points?
You can say so. You can say so. But now let me just show you what are the difference if you look at the weighted like the projectable line. So now just let A and B are not equal 1, for example. So say A equal 2, B equal 1. So now you know it is now different, right? So that we now change the group action. So group in our context is still just S1. And we act on S3 in C2. And as you know, if we have this guy, then we just define this as a e to the a. So let me say from I a t z1 e to the I b t z2 defined like this. So with the concrete like the example, we know e to the 2it z1 e to the it z2. So we define this action, and you will know that still it satisfies the or purpose that the requirement of the group action. That's fine. So that you still make the quotient. Now it depends on this A and B. So previously this A and B exponent are all just equal 1, but now you know it's now different. Is that okay with you? So that still you can write this as a Z1 versus C2 as a one element, where Z1, C2 is in S3. Right? But the meaning of this, like the set is now different. Can you see that? So that this guy is no longer lambda times Z1, lambda times Z2. They're now different. So that you need to now put A and B here. Is that okay with you? A and B here. So why this like the caused the like the issue. So now you can see that previously you can now easily see that this would be same as a Z1 over Z2 versus 1 if Z2 is not 0, and this also equals 1 versus Z2 over Z1 if Z1 is not 0. So previously, so for A and B are equal 1. Are you with me up to here? So that means that if you now draw the Bloch sphere, which is a smooth manifold, so S2 Bloch sphere. So I think I explained this part, but I actually didn't assume you really digest completely because it takes time for everyone. So even for very like the clever, like the genius, like the kids, that's always the case. So let me just re-explain this part. So please just follow this part carefully. So you should understand this picture in this like the context in the following way. So if you wanna like the discuss with either the ChatGPT or any those like the fancy like the AI like the support, you can search so-called a one-point compactification, whatever that is. So this is just a term. So I just provide this so that you can just later search it. So you start from the plane C1, okay? And then you add the point at infinity. Again, I know I explained this before, but I just want to make sure that you really digest. So if you start from the 0, then you take the open subset. So this C1 is now the just open ball with the radius equals just infinity. So smooth manifold. So you just take the coordinate by Z. The Z means, so you start from Z that equals Z versus 1. And now you'd like to add the point at infinity. So you know this, so that you make this guy. This is called the Riemann sphere. What does that mean? So that means that we'd like to change this infinity as a 1 versus 1 over z. So now you can change from one to the other in a sense that if you start from here, you make the coordinate by z, starting from the south pole. Then you add the point at infinity and make the sphere. And you add the north pole as a point of the infinity. Are you with me? This point is now written as a 1 over z. 1 over z was not in the plane before. So you identify each like the element by z. But now you add the additional point, then this corresponding north pole should be written as a 1 over z. This 1 over z is coming from the expression of the z1 versus like a z2 in a sense that this is now identified by z. This is now identified as z1 over z, right? So we just go from one to the other. But you can just transfer in this way globally. You know what I mean? But if you change the exponent, not like this, then the situation will change. So now let me just give you the different situation. For A equals 2, B equal 1, let's see what happens. So now you can see. So if you start from Z, then if I just play the same game, I should get this guy. But what is the definition? So this is defined. So previously, this guy was defined by what? Lambda Z comma lambda. Do you agree? Lambda z comma lambda. Lambda was arbitrarily complex number except 0. This is the definition. Are you with me? But now it's just changing. So it is lambda square z with lambda. Are you with me? Because now the exponent now play a role. So let me just put the different color. So this a is now 2. So that no longer you cannot write this guy as a 1 versus 1 over z. This was allowed in a sense that in this case, you just choose, for example, lambda equals 1 over z. Then you get 1 comma 1 over z like this, for example, right? So that you can go from one to the other previously, but now the exponent are no longer the same, so that you cannot change from one to the other in a sense that z transfer as just a 1 over z. That's not allowed. So that causes the following like the issue. So if you still draw the sphere, this still is allowed, but now you have a south pole and north pole. This 2 point becomes singular in a sense that there's no way to find the small neighborhood. There's no way to find any of the neighborhood that can be identified as a ball in R2. That's not possible. Only it is allowed to make this be so-called a R2 quotient out by Z of something like this. R2 quotient out by Z of the something. So yeah, go ahead.
When I was using ChatGPT to do the prompt set, it just from what I could tell, it described like it having the singularities having non-trivial orbits,
Hmm.
basically meaning it ended up repeating at one point. It repeated itself in that neighborhood. Is that why there's like the Z mod A? Because if you do A multiple times, it will loop back to the same point every A.
You can say so, but it's really hard to draw the like the picture to describe everything explicit. But let me just say in word, and if you have any like the points to clarify, let me know. So for example, what's the point of the S2? It's actually the orbit in S3. You agree? So each of the orbit, great circle in S3 correspond to the point of the two-dimensional sphere. Are you with me? That was our previous understanding of the Hopf vibration before. But if you choose A equal 2 and B equal 1, what happened? If you rotate one time, so the first component actually rotate twice. Do you agree? And then you use that as a one gray circle, but the gray circle is now changing. So if you just collect them, so it's now not the same as topological as S2, but it's some like the weird 2 point actually appear that correspond to the south pole and north pole. That's what I'm saying. So if we identify, so let me just repeat. So it's very hard to imagine, but this is mathematically like the situation, eventually it happens. So if we identify gray circle as a 1 point, the collection of that point becomes the two-dimensional sphere. That's the whole vibration. And we say that's the Bloch sphere. But if you change the exponent A and B, then it's not no longer just a general like the gray circle. It actually rotates something crazy. Does that make sense to you? And if you just to consider that as the element and collect them, this is no longer same as just a usual like the two-dimensional sphere. But those like the two that the weird like the effect appears on the north pole and south pole at the same time. That means that so those 2 points you cannot find any small neighborhood that is identified as a ball in R2. That's not possible. That's not allowed. If that's the case, then there's no such like the effect. So you can kind of just assume that so this like a picture only happens for A and B equal 1, so that you can always find small neighborhood that can be identified as a ball in R2. That's the smooth manifold, and that's coming from the global like quotient. However, for the changing the exponent, you can now see that there's no way to change from one to the other in this way. That's not allowed. Can you see that? And that effect would be like the recorded on only these 2 points of the south pole and north pole, so that you can say this is now the concept of what? Smooth manifold with singularities, meaning that at least you can find finitely many points such that you are not able to find the small neighbor of those points that are identifiable in R2. Is that okay with you? And in this like the case, these two are the north pole and south pole. And now this is a fancy term called the so-called the Orbifold. I highly recommend you to use this term in presentation. So math faculty will very like this term in a sense that they know how fancy this term is. So let me just repeat. So what's the definition of the manifold? Locally Rn, meaning that for each arbitrary point on the target space, you can find a small neighborhood that can be identifiable in the Euclidean space. What is the concept of orbifold? So that's allowed for the general cases, but there are still exceptions that you cannot do that. So that we need to treat those points as exceptions. That's the concept of the Orbifold. So the Orbifold is the generalization of the manifold or the smooth manifold. So that's part of the explanation for the Orbifold. So you can simply just put just a one sentence. So previously, the collection of the one qubit is what? Smooth manifold. Now, from the context of the quantum computing, we change the structure as a manifold with singularities. And mathematically, that's called by the Orbifold. That's it. Yeah, that's the one part of the clarification regarding the Orbifold and the global, like the quotient. What is the global quotient? We can already change the z as just 1 over z, but from the different exponent, that's not allowed. You cannot do that. Is that okay with you? So that's the global, like the quotient.
Wait, could you repeat the definition you said for global quotient one last time? Sorry.
So the global quotient here means so this is the notation of the quotient. And in the like the usual exponent a and b are one, in that case, you can always change z versus one as a one versus z. Sorry, one versus one over z for a and b equal one. But if you just track the form of the z1 versus z2 with a different exponent, that's not allowed. Meaning that you cannot change from the south pole to the north pole in general. So that even though we are taking the quotient, but you cannot just reflect that effect on the south pole and north pole at the same time. You need to treat them separately. So that's we call the so-called the local like quotient, not the global quotient. Still, we quotient out by S1 separate like the individually. That's correct. But previously, when we talk about the like the Bloch sphere, we didn't really treat it as a local object. It's a sort of the global. So that's why we call it by the global quotient. Is that okay with you? What I'm saying is that this means that we change the coordinate from the south pole to north pole. That's the meaning. So that we are looking at the effect of the 2 points at the same time.
Is this something like the affine charts I heard about a bit?
Yeah, that's also related. So this is also part of the question from Evelyn. So it's about the chart. Second, like the point is chart and affine chart. So let me explain this. So given a smooth manifold, any smooth manifold. So what's the definition? So that if you choose the point, arbitrary point, then you are able to find the small neighborhood contain. This is the open subset containing this V that you are able to identify this as a ball. So this Q P maps to zero for simplicity, so that this is always allowed. Is that okay with you? So we call this map chart. This is the definition of the chart. And usually the inverse map is called the coordinate, or many people call it by the local coordinate. So this is just the inverse map. So it's just the name of the function from one to the other in a way that, so I just give you the definition that each point, so manifold just means, so each point so that you can just identify. Identification just means that you can find the inverse. That's it. Is that okay with you? Inverse, as long as there's an inverse mathematically, that means that it should be one to one and also one to, right? One to correspondence. That's the meaning. So that's the chart. Is that okay with you? So the next, like the term is about the what is the smoothness here? Smoothness. So let me ask you this. So from one variable calculus, if the so because you definitely studied AP calculus before, if the function is differentiable, that is what? Continuous. Do you agree? As a fact. But the converse is not the case, such as the absolute value function. Are you with me? So smoothness means that this chart and local like coordinate, these two are infinitely differentiable. So we do not care the order of the differentiability. That's the meaning of the smooth manifold. Smooth is same as infinitely differentiable, meaning that you can take the derivative as much as you want. That's the meaning of the smoothness. Infinitely differentiable regarding charts and local coordinates. So for example, if we say, so for, I don't know, for Jason, so people also call topological manifold, meaning that we don't care the differentiability. Only this map should be just continuous. So it just depends on the context, but we want to do the calculus. In that case, we want to just allow to get the differentiability. So, and we usually do not want to care the order of the differentiability. So that's why we call the smooth manifold. Is that okay with you? That's the clarification of the chart. Then what is the affine chart? So that's just a context from the CP1. So from the CP1, so this is the collection of the Z1 versus Z2, as you know, right? So Z1, Z2 in, let me say in Z2, that's fine. So affine chart is a special case. So there are two affine charts. So, and this is also called by the inhomogeneous coordinate. So when I say they are the same, meaning that, so in terms of the map, the direction of the map, so they are not exactly the same, but those are two are just a way to identify from one to the other. That's what I'm saying. So usually geometers never actually care the direction of the map. So like a domain and codomain, because they are just one-to-one correspondence. So this means the following. So first, like the chart, so let me call by V1 and V2. That's good for you to understand. So this is same as a Z1 versus, so let me write down V2 later on. So this is not you. You already saw it several times. Z1 versus Z2, saying Z1 is not zero. So V2 is collection of the Z1 versus Z2, that Z2 is not zero. Then let's play with it. So then you know this is same as 1 versus Z2 over Z1. You agree? So that now you can see that this is just collection of the Z1 versus Z2 over Z1. You agree? Because the other component is 1, so we don't need to care. By the way, you can see that Z2 over Z1 is what? Just this complex value. Do you agree? Because Z2 and Z1 are arbitrarily like the value, complex like the value, but we just allow this Z1 is not no longer zero. That's it, because we know the denominator cannot be zero. Is that okay with you? This is now same, it's just Z1. Because Z2 over Z1 can be any value, basically. So this is first open subset, and V2 is just the same as Z1 over Z2 versus 1, the same condition, so that you can also see that this can be identified Z1 over Z2 in C1 with the same condition. This is also same as C1. So you should interpret these two. So these two are the affine chart. We usually call this by either the affine chart or the inhomogeneous coordinate. You can use any terms. So the expert understand what people are talking about. So picture in this case is clear because you already know this picture. This is all you need to know. So this means the following. So if you start from here, so let me draw three different like, pictures. CP1, smooth manifold. You start from here, okay? And then you choose 2 points. One is the south pole. Another one is the north pole. These two are the target points. Then what you do is you want to forget about this point. When you choose the south pole, if you look at the north pole, you forget the south pole. Then which coordinate you can choose, which chart you can choose. Just to forget about this north pole from the south pole, what do you get? So that you get this guy. Do you agree? So each point now correspond to Z2 over Z1. That correspond to here as a Z1 versus Z2. Can you get that? That's the picture correspondence from here. You know this guy is identified as this guy. Can you get that? And if you start from the North Pole, then you also get another like the plane. Then you have either the complex value given by Z1 over Z2 that is the same as Z1 versus Z2. So that these are just a concrete like the example of the chart that we simply just call by the affine chart. So let me just repeat. So if you have a global like the manifold structure, then you have each point as a Z1 versus Z2. Then you just choose the affine subset as either this C1 or that C1. So each element is complex value, then you know how to identify as a just point of the sphere. This kind of is fancy, I know it, but yeah, you can follow it. So I assume I clarify the smoothness, singularities, chart, vibration, global quotient, Orbifold up to here. Any other comments up to here? Just for the record, just one thing. So about the abstract algebra. So even though we are treating everything very like the geometric, so so in fact, it turns out. So let me just put this term. It turns out that the geometric structure of a Hopf vibration pi from S3 to S2 is the same as understanding. Understanding is not very like the concrete, so same as the, let me say concretely, ring structure of the polynomial ring C with the x1 and x2. So this is just a polynomial over complex with x1, x2 indeterminates. Let me say just variables. So it turns out that, so this is very useful for the algorithms and the mathematical abstraction for the number theory or like the algebraic geometry and so on, that even though we are saying everything very geometric, but when one like the conquer like the algorithm, then one can actually just look at the just a collection of the polynomials because the amount of the information is turns out to be exactly the same. So that there's just a way to make all like the data in a way that one should not lose any like the necessary like the information, but still one can just proceed the addition, subtraction, multiplication, division to just transfer all necessary like the data. But this is a kind of a fancy understanding. And ZX calculus is sort of related, but that's not exactly we need. So up to here is the part I want to make the record. If you have no other questions up to here. I know it's already like a heavy for the Friday, like the evening. I know it. Yeah, sorry for that. Let me stop the record here.